we're asked to consider the following rational functions. So we've got rational functions, so they can be written as a fraction. So we've got r of x, s of x, t of x, and u of x. Which of these functions has a horizontal asymptote? Which of them has a slant asymptote? Which of them has no vertical asymptote? And we need to graph one of them. All right, so let's start with A, looking at which of the functions has a horizontal asymptote. So an asymptote is this blue line that you'll see here. And it's a line that because it's horizontal, and you can see it's like at a particular y value, as x is getting closer and closer to infinity, you can see the x value is getting higher and higher and higher. The y is getting closer to this value. You could look at this other horizontal asymptote over here. As x gets closer and closer to negative infinity, it's getting bigger and bigger and bigger in the negative direction. The y keeps getting closer and closer to this line, to this y value. So we have to check, do any of these functions actually approach some y value as the x gets bigger and bigger? So looking at r of x, we have 2x minus 1. Imagine x is 1 million. 2 million is going to be pretty much the same as 2 million minus 1. So that's why we've crossed off this 1, because it really doesn't matter when x is close to infinity. Same thing down here. Like this 2 obviously isn't going to matter when we're close to infinity. And even if you look at here, x squared versus x squared is going to grow so much faster than x that when you're close to infinity, this x isn't even going to matter. So when we're looking at rational functions, we're really only looking at the leading term in the numerator and the denominator. So now to clean this up a little, if we're looking at r of x as x goes towards infinity, 2x over x squared, let's think what is going to happen to this rx value, our y value. Well, which is going to grow faster? This x squared is going to grow way faster. So what you're going to end up with is a fraction that has a small numerator and a huge denominator. Okay, so this is going to end up being a tiny fraction. This is going to be a super small number. And as you get closer and closer to infinity, this fraction, say this is 1, and then it's going to be smaller and smaller and smaller and smaller and smaller and smaller, and it's going to go towards 0. It will never touch 0 because it's always going to be a fraction, but it'll get a tinier and tinier fraction. So whatever this function is, we know that as x goes towards infinity, y is going to approach 0. So we know our asymptote is going to be along here. And we don't know whether it's from the top or the bottom, but we do know that it's going to approach 0. So if it's approaching some value, including 0, that means it has a horizontal asymptote. So r of x does have a horizontal asymptote. Okay, so now we can check s of x in kind of a similar fashion. So s of x equals x cubed plus 27 over x squared plus 4. So let's just check as x goes towards infinity, what's going to happen? Well, if x is going towards infinity, we couldn't care less about these numbers. They're not going to really affect it very much. So now we're just left with x cubed over x squared. So you have to ask yourself, which one is going to grow bigger? Well, x cubed is going to grow a lot faster than x squared. So you're going to end up with, as x goes to infinity, a huge number. S of x is going to be a huge number over a smaller number. And as x goes to infinity, this is just going to get bigger and bigger. The huge number is just going to get huger and huger. So that means, and this x squared will never be able to keep up with x cubed. So if we look at this one, as x goes to infinity, y is going to go to infinity too. They're both getting bigger. Okay, so this does not have a horizontal asymptote. It's not like it leads towards some y value where it caps off. It's not like there's like a line here. It just keeps getting bigger. So no horizontal asymptote for s of x. Okay, we're making good progress here. Let's check t of x as x goes to infinity. So let's see. T of x equals x cubed minus 9x over x plus 2. So first step, we get rid of everything but the leading term. As we think about x going to infinity, as x goes to infinity, we have to think which one is going to grow faster than the other one as x gets bigger and bigger. And we see that this x cubed is going to grow faster. So then we're going to end up with a huge number over a smaller number as x is going towards infinity. As x is going to infinity. So this t of x is our y value, the value of the function. So that means, this looks kind of familiar from the last one, as x is going towards infinity, y is also going towards infinity. Now, I just realized I actually made a mistake on s of x. So I checked as x goes to infinity, but if we look here at our example, you could also have an asymptote as x is going to negative infinity. So we need to also check as x is going to negative infinity. So going back to s of x, if we have s of x as x is going to negative infinity, we have, again, we can disregard the leading term. So we just end up with x to the cubed over x squared. So with x going to negative infinity, we'd have negative x cubed over negative x squared. So this would be the same as negative x cubed over x squared. But so this is going to be a negative number overall. But when we look, we see this is still going to grow faster. And when we have the bigger one in the numerator, it's going to trend towards infinity. But this time it's going to trend towards negative infinity. So when x goes to negative infinity, y goes to negative infinity. And again, we have no horizontal asymptote. It's not like it's approaching something. So we can do the same thing here. And we see s of x as x goes to negative infinity, I didn't write that very neatly, sorry, is going to approach x cubed over x. And then if x is going towards negative infinity, then we will have negative x cubed over negative x, and that will be the same as x cubed over x, which will go towards infinity. So we'll also have y going towards infinity as x goes to negative infinity, but either way, we have no horizontal asymptote. Okay, so we can see from these examples that if you have the numerator growing faster than the denominator, it doesn't really matter whether x is positive or negative in terms of a horizontal asymptote. All that really matters is whether it's headed towards a number or not. So if it's going to negative infinity or positive infinity, we don't really care. All right, we're almost done with part A, so let's go ahead and check u of x. Okay, so u of x equals x squared plus x minus 6 over x squared minus 25. So as x goes towards infinity, well, these aren't going to matter so much. And then we're just left with x squared over x squared. Okay, so x squared over x squared, if x is 100, and then squared over 100 squared, that equals 1. X is 2,948 squared over 2,948 squared equals 1. Okay, so if these ones aren't mattering so much, what we're left with is always 1. Okay, so that means as we get closer to infinity, that means our graph will be approaching 1. So our horizontal asymptote is right here at 1, and I'm not really doing a nice job to graph this whole thing, so I don't know whether it approaches it from the bottom or the top. We could figure that out, but I'm lazy right now. But we do know that it's approaching 1. And we can see that it has a horizontal asymptote, and that's all the question is asking, so we don't need to check the negative. All right, so then if we're looking at, so this one does have horizontal asymptote. So the question is asking which one has a horizontal asymptote. So we have r of x, and then we have none, none, and then this one has an asymptote. So the answer is r of x and u of x have horizontal asymptotes. And we solved part A.